All right, let's go over these. So at the end of last class, we looked at this reaction, right, where we're taking water and an aldehyde, and when we mix them together, we're going to form, to some extent, an aldehyde hydrate, which is the product on the right. Right. When we drew the mechanism for this reaction, we pointed out that the only atoms involved in this mechanism are going to be the carbon of the carbonyl, the oxygen of the carbonyl, the hydrogen of the water, and the oxygen of the water. Right? So those are the only atoms that you have any business drawing arrows from or to. All of the other atoms in this reaction stay exactly the same. Right? If we look at this reaction up here, you can see even though we're starting with a different functional group, right, a ketone rather than an aldehyde, we still have those same four atoms. Okay, and this carbonyl even though it's a ketone, is going to react in the same way as an aldehyde. Right? We talked at the beginning of the semester about the structure-function relationship. Right? The structure of a molecule, the structure of a functional group, is going to determine how it reacts or how it functions. Right? With carbonyl compounds, the main theme in those structures is the fact that we have a carbonyl bond, a carbon double bond oxygen. Right? That carbon is electron deficient, the oxygen is electron rich, so anything that has electrons is going to react at the carbonyl. Right? So ketones and aldehydes are going to react more or less the same way, right? But the structures are going to be different because they're slightly different functional groups around the carbonyl. So on Monday we went through a mechanism. It started off with an acid-base reaction. Right? And before we started the mechanism, we took stock of the changes that were being that the molecule was undergoing as it goes through this transformation. Right? So in order to get from the starting materials to the product, we have to break the carbonyl pi bond. Right? We also have to break an OH bond on water. Okay? At the same time, we have to be making these two bonds. So we're making a new carbon-oxygen sigma bond, and we're making a new oxygen-hydrogen sigma bond. All right? So when we went through the mechanism on Monday, we started off by taking the oxygen of the carbonyl, right, and making our new oxygen-hydrogen sigma bond. Right? And at the same time, because this hydrogen can only hold 2 electrons, if we're putting 2 into this hydrogen, right, then we have to break 2 electrons away. Right? We can't have a hydrogen with 4 electrons around it. And you can see each of these arrows are starting at a pair of electrons. First arrow is starting at a non-bonding pair in oxygen. The second arrow is starting at a bonded pair in a sigma bond between oxygen and hydrogen. Right, and so the second arrow illustrates breaking of the OH sigma bond. Right, so that gets rid of 2 of the steps, 2 of the things that we need to do in order to get from starting material to the product. Right, so we gain a new oxygen-hydrogen sigma bond. Oxygen is going to be positively charged. And then the water, oxygen lost a proton, gains an extra pair of electrons, and we'll have a formal negative charge. Okay, questions about this? Okay, so when I draw these arrows, so this is just an acid-base mechanism. We've been looking at these now for I guess about 2 weeks. All right? When I draw these 2 arrows, unless I use both hands, I necessarily have to draw 1 arrow first, right? But in reality, these 2 arrows being in one step indicate that these electrons are moving in concert, right? They're moving all at the same time. So it's not like oxygen is reaching out and bonding to the hydrogen, and then hydrogen is releasing that bond, right? both of these things are happening at the same time. As the oxygen is reaching out to get protonated, that proton is losing that pair of electrons and giving it to the other oxygen, right? So all of that electron density at one time is kind of being shifted from one part of the molecule to the other. All right, the second step of this reaction is going to show the formation of the carbon-oxygen sigma bond. Right, and then because this carbon has 8 electrons around it, if we're going to form a new bond to that carbon, we have to break a bond already there to that carbon. And so the weakest bond there is going to be carbon-oxygen pi bond, right? And so that's going to show the breaking of the carbon-oxygen pi bond. Right? Again, I'm drawing 2 arrows, but all of that electron movement is happening at the same time. Right? It's not that we're making a bond between oxygen and carbon first, and then once that carbon realizes, oh shit, I have 10 electrons around me, right? It breaks a bond, right? Everything's happening at one time, right? And this explains how we get to the ketone hydrate. Right, so you can see, even though we're starting with a different starting material, a slightly different functional group, right, the same atoms apply. The same mechanism that you would draw for an aldehyde hydration, you would draw for a ketone hydration. Right, questions about this? Yeah. So this mechanism that we just did, right, these are going to be what we do in step 1. This is what we're doing in step 2. Right, but we can reverse these. We can show how maybe we break the carbon-oxygen pi bond first, right, making a new carbon-oxygen sigma bond, and then do the proton exchange or acid-base chemistry in subsequent steps. So let's take a look what that would look like mechanistically. Right, so if we're going to show the formation of the carbon-oxygen sigma bond first, we'll take water, right, and use that water as the Lewis base and add that directly to the carbonyl carbon. Right, if we're making a new bond to this carbon, we have to break an old bond. Right, so we're going to break the carbon-oxygen pi bond. So keeping track, that carbon-oxygen pi bond is the one that was formed, right? So we took the lone pair of electrons on water, and those are now caught up in this carbon-oxygen sigma bond, right? Oxygen lost a pair of electrons, the oxygen and water lost a pair of electrons, so it gets a formal positive charge. Right? And then the other oxygen, those pi electrons that were between the carbon and oxygen, are now a lone pair on the other oxygen. Okay, so you can see as we're doing these, you should see a pattern, right? Every time we're making a bond, we're also breaking a bond. All right, what's the second step? Who can describe what's going to happen in the second step? Yeah.
You would break one of the bonds on the OH and put it onto the oxygen, and then that would create a lone pair, and then you would take the lone pair on the other oxygen and connect it to the H.
Good. Right, so we needed to break an OH sigma bond, and we needed to make a new OH sigma bond. Right, so the proton from what was water, right, gets plucked off that oxygen, giving that oxygen its lone pair back, right? So now it's going to become neutral again, have 2 lone pairs. right? And the oxygen then has an extra lone pair. That extra lone pair is now a sigma bond between oxygen and hydrogen. Yeah.
Do you need to write proton transfer above the yield arrow?
No, I wrote that because we're going to talk about this step in more depth. Any questions? Any other questions? Okay, so this is how we can explain how we get from the starting materials to the products, right? How the electrons are moving. In the second mechanism, though, there's a problem. And this problem comes back to our understanding of orbitals and how orbitals have to interact in order for bonds made and bonds to be broken. Right? And that is, in the second step, it cannot happen this way. Right? Technically speaking, it does not happen this way. You can't get direct transfer from a proton on this oxygen to a proton on the oxygen next door. Right? And let's talk about why that is. Okay, so I'm going to just show an acid-base reaction. Right? The acid in this reaction is going to be ethanol, and the base in this reaction is going to be lithium dimethylamide. Right? Don't worry about the lithium. The lithium is just considered a spectator ion, right? So it's just kind of hanging out, counterbalancing any negative charge that's in there, right? But the base is going to be a nitrogen that lost a proton, so it has 2 pairs of electrons and a formal negative charge. So a pretty strong base in this case. Right? If we wanted to show the mechanism for this acid-base reaction, we would show a pair of electrons from nitrogen reaching out, grabbing a proton, right? And then the OH sigma bond breaking, and that would lead to the alkoxide. And then the dimethylamine. Right, so we're just taking a proton off of the ethanol, sigma electrons stay behind, and that proton ends up on the on the negatively charged nitrogen, so now that nitrogen becomes neutral amine. Okay, everybody can follow us? Any questions? All right, so when we looked at acid-base chemistry, we also looked at how the orbitals have to interact in order for this acid-base chemistry to occur, or for any bond formation to occur. And we understood that the filled non-bonding orbital of the base always has to interact with the anti-bonding orbital of the acid. Right? So that's the OH sigma star. I'm going to get rid of this mechanism arrow here just so it's not so cluttered. Right? And then we have an sp3 non-bonding orbital on nitrogen. Okay, and so those are the 2 orbitals that have to interact in order for that NH bond to form and for the OH bond to break. Okay, how do these molecules have to approach each other?
With the correct orientation.
With the correct, and what is that?
Like this.
Good, right? So the orbitals interact head on, right? So whenever that nitrogen adds, right, I'm just going to draw it at a slightly different perspective, right? These orbitals have to overlap head on. So the the non-bonding orbital of nitrogen has to come straight into the anti-bonding orbital of the OH bond of the acid. Right? Okay? If this orbital attempts to come in from any other direction, that bond is not going to be formed. You're not going to get effective orbital overlap. Right? So whenever these molecules interact, they're always going to approach each other from the same direction, and it's a direction that lines up those orbitals. Right? Here we have the same situation, right? Different atoms, different molecule, right? But the same sort of situation where we have a non-bonding pair, this time on oxygen, right? That's going to act as the Lewis basic pair, okay? And then we have our hydrogen, a proton, on an oxygen next door, right? And that proton gets transferred. So when you look at this drawing, what is the problem going to be with carrying out that proton transfer? Yep.
The overlap of this or the sigma anti-bonding orbital can't like switch around.
Great, yeah, so it's going to be impossible for this oxygen here to approach this OH bond directly from the antibonding orbital, right? So the orbitals that need to overlap in order for that proton transfer to occur cannot overlap. Just spatially, right, in terms of bond angles, they cannot approach each other from the correct angle. Right? And if you count the number of atoms, right, that are in this kind of cycle that are interacting, we have 1 oxygen, 2 carbon, 3 the other oxygen, and 4 the other hydrogen. Right? So if you think about a 4-membered ring and how much strain and tension there is on that 4-membered ring, how much it wants to open up, this is kind of the same situation, right? We have 4 atoms, we need to connect atom 1 to atom 4, and we're losing a bond at the same time. Right, but kind of in the middle of that, we're going to need to form a 4-member transition state. Not possible because these orbitals are unable to interact in the way that they need to. All right, so that produces a problem here for this mechanism. Right, if this can't happen, how do we get the proton from one oxygen onto the other oxygen?
Do you have to break the sigma bond between oxygen and carbon?
Here or
I
here?
was thinking the other one.
Yeah, that's not going to happen because we need that bond there, right? If we're right?
Just a guess, could you interact with other water molecules?
Awesome, right? So, you know, when we're doing these reactions, we don't just have 1 molecule of ketone and 1 molecule of water, right? But we have trillions of molecules of ketone and trillions of molecules of water. Right, so there are going to be other molecules in this that can help out and act as a shuttle for a proton, right? So when we're starting here, we're not going to go directly from this intermediate to the product, right? But instead, what we're going to do is we're going to get another molecule of water, right? Not a bad base, and that molecule of water is going to pluck a proton off. Right, that's going to form a second intermediate. right? So here's our water that we just protonated, all right? And then here's the molecule that we just deprotonated. Okay. And then in a second step, we're going to take the basic oxygen that we want to protonate, all right? And this water is essentially just acting as a shuttle to take the proton off of one oxygen and allow it to get to the other oxygen. Right, so we would show the new bond formation, OH bond formation, and then the old OH bond breaking. Okay, so that four-member transition state intermolecular proton transfer is not allowed. We need to use another molecule to help facilitate that proton transfer. Questions? Yeah.
If they were farther apart, would it be possible to then bend it around?
It would be, yeah. So if this was like a 5 or 6 member transition state, right, where we had more atoms in between, that intramolecular transfer could occur. But specifically, these four member rings, they can't work like that. Good question. Yeah.
So then in mechanism 2,
Yes.
where we have the ketone and then the double bond, like pi bond breaks, and when the new substituent attaches, like you have in the second step, you have the positively charged oxygen. So where does the other hydrogen go then if you're using another molecule of water?
So where does this hydrogen
Yeah.
go? Yeah, so that's now this molecule. So if water plucks that proton off, it goes from H2O to H3O plus.
Okay.
All right, and so that proton, right, if we want to circle it just to account for it, right, that proton starts here, now it's here, and then it finally ends up there.
Okay.
Make sense? And we're not, we're not saying that this specific molecule of water, right, is going to become this specific molecule of hydronium, right? This might float away and go to another molecule, but we're going to have hydronium in there in order to protonate. Other questions? Right, so hopefully you can see how your knowledge of orbitals, right, your knowledge of bonding geometry applies to our understanding of these reactions, right? It's important that we understand the shapes of molecules. It's important we understand where the electrons are and where the electrons need to go in order to explain how these molecules are interacting with one another. All right, so we're going to take a look at some energy diagrams for these reactions. You guys have seen reaction energy diagrams before, hopefully in ICP. Right? It's just tracking the kinetics and thermodynamics of a reaction, right? So the energy levels of the reactants, the products, or the intermediates, right? And it also shows you activation energy for each step, right? And so what we're doing is we're just plotting the reaction coordinate, or just the course of the reaction, right, against the energy. So we're going to say in this reaction that this is going to be an endothermic reaction. Right? And so if we're numbering things, naming things, right? This is going to be the cyclopentanone and water. Right? Over here, this is the product of the reaction. Okay, and you can see in the mechanism we're creating one intermediate, so we need to reflect that one intermediate in the energy diagram. Right? When we think about energy diagrams, we're going to be considering two aspects of the reaction energy, and that's going to be the thermodynamics of the reaction and the kinetics of the reaction. Right? And I want to make sure that we're all on the same page in understanding what these two terms are referring to, thermodynamics and kinetics. Right? So when we're talking about thermodynamics, thermodynamics relate to the reaction equilibrium. Right? And really only focus on the energy of reactants, products, or intermediates. Right, so when we're looking at this reaction, right, when we're considering the thermodynamically what's occurring, right, we're only thinking about what's the energy difference between the starting materials and the intermediate, right, or what's the energy difference between the starting materials and the product, right? Ignoring any route, how we get from point A to point B, right, we're just thinking about the energies, right, whether it's exothermic or endothermic, right? You can see in this reaction, it's going to be a positive delta G, right? And so it's going to be an endergonic, right, or endothermic reaction, right? An uphill reaction. Thinking about the kinetics of a reaction, right? We're thinking about how fast that reaction is going to go. Kinetics have nothing to do with equilibrium, right? Kinetics don't speak to how much of the product versus how much of the reactant, right? It's only a consideration of how fast that reaction is going or the rate of the reaction, right? How frequently molecules that need to interact are actually interacting. Okay, and so when we're thinking about kinetics, we're not looking at the energy levels of the reactants, products, and intermediates necessarily, right? But we're really focusing on the pathways in between those things. Right, so you can see here in purple, I've drawn the pathways. One is going to be higher energy pathway than the other. We'll talk about why that is. Right, the absolute height of each of these pathways we refer to as transition states. And we represent that transition state with these double daggers here. Right? Whereas reactants, products, and intermediates are all real tangible things. We can observe them, we can analyze them, right? A lot of the times intermediates are very fleeting. They won't last very long, but we can prove that they exist. Transition states are going to be theoretical. We can represent them or illustrate them on a piece of paper. So if we think about, in this first step, how we actually get from the reactant to, or the reactants to the intermediates. Right, we would represent the transition state like this. Okay, and so this is meant to show at the highest energy between the reactants and the intermediates, right, the highest energy level in that pathway, right, we would expect the OH, the new OH bond to be forming at the same time as the old OH bond is breaking. So what we're going to do when we draw that transition state, we're going to draw any bond that is being formed or being broken as a dotted line. Right, to show that it's not really there, but it's also, you know, forming, so it's coming into being. Okay. The other thing that we're going to show on our transition states are any charges that are going to be forming or that are going to be disappearing. Right, and when we show those charges, we're going to draw them in parentheses. Right, because it's not a full. If it's in transition, right, it's not a full formal charge, but it's more than just a partial charge. Right, we can say that it's kind of a half charge. As it's being formed in this case, right? So the OH ends up with a negative charge. So in the transition state, we would draw a negative charge in parentheses on the oxygen. That's going to get the full formal charge here, right? And then the oxygen of the carbonyl, that's giving away a pair of electrons, it's going to become positively charged. So we'll put a positive charge in parentheses next to that oxygen, right? And this just represents, in theory, right, when this reaction or this step is occurring, These are the bonds that are being made, bonds that are being broken, and these are the charges that are going to form in that process. Okay? All right. When we look at the energy diagram for this mechanism, there are two transition states. You can see that one is a higher energy transition state. All right, and so we would refer to this higher energy transition state as the rate limiting step. Of the reaction.
Does this kind of refer to like the slow and fast step mechanisms?
Perfect, yeah. Right, so this tells us that this first step, right, the proton transfer from water to oxygen, right, that's going to happen, say, 100 times a second, right, at the initial part of the reaction. I'm just throwing out numbers here, right? Happens 100 times a second. Second step, because it requires more energy, maybe it only happens 10 times a second, right? So overall, the overall reaction rate, right, it doesn't matter if this is faster, right? This doesn't matter, you know, how many times a second it happens. This is the step that controls the rate of the reaction, right? If this happens 100 times a second, then all we're doing is just building up intermediate until this second step can occur, right? So the highest transition state represents the rate limiting step of the reaction. Okay, what I want to make sure you know is why the second step is higher in energy than the first step. Why does it take more energy for the molecules to react in that way and less energy for the molecules to react in that way?
Is it the probability of the orbitals lining up?
What do you mean by probability?
So how easy it is for them to like align in a way that a bond would form?
Okay. I mean, I would say it involves the orbitals, yeah.
Does it have to do with the pi bond or the breaking of the pi bond?
In a way, I guess. I mean, just think about this. I mean, you know, all of the, you know, when you talk about energy in this class, it really all comes back to the electrons, the orbitals, the amount of strain within a molecule, the amount of strain between two molecules. Right? So why is it easier to pluck a proton off of a molecule than it would be to form a carbon-oxygen bond?
So yes, the intermediate has more branches if you see. Maybe that increases the strain there.
So whenever we add to a carbonyl, remember, okay, we have to make sure that we're overlapping the correct orbital. So if we're adding to a carbonyl carbon, breaking the carbon-oxygen pi bond, right, the orbital that the electrons are being added to are going to be the pi antibonding orbital. Okay, just like whenever we break an OH sigma bond, we are putting electrons into the OH sigma antibonding orbital. Right? So why is it easier to add to this orbital, harder to add to this orbital?
The P bonds are higher energy.
Okay, p bonds are higher in energy, but why does that matter?
Is it the hybridization?
Hybridization has something to do with it. Anybody else?
That's just more electron.
What's that?
That's just a big electron cloud right there. You
Awesome,
don't have
right?
for that.
So on this molecule, we have hydrogens here and here, right? Hydrogens here and here. Okay, so if we're thinking about plucking a proton, Protons are always on the outsides of molecules. That means that the antibonding orbital that we have to interact with is also going to be on the far outside of the molecule. So for a base to come by and pluck off a proton, it really doesn't have to interact with the rest of the molecule at all, right? Because the proton's on the outside, just kind of has to swim by, right? If this is the proton, has to swim by, just pick it up, right? And move on, right? If I have to interact with an atom that's over there, okay, now I gotta climb the table and spend a lot more energy getting to that orbital. This is the same thing, right? This orbital, it's higher in energy for sure, but there's a lot more stuff around it. There's a lot more cabbage around it. So in order for the HO to interact with that orbital, it has to maneuver around more stuff, and there's going to be a lot more electron interaction, right? So as a result, acid-base reactions have a very low kinetic barrier, usually, right? Unless it's really specialized acid. That means there doesn't involve a lot of energy for those molecules to interact, because the protons are always on the outside of the molecules. Antibody orbitals are easy to get to, right? Carbonyl addition is going to be much higher in energy in terms of that orbital overlap, just because the orbitals are less available. Right? It's harder to interact with those orbitals. Okay, any questions about this? Okay, we'll end there. Come back and talk about this reaction even more on Friday. No, I don't know.